All right. I don't know what happened. The stream suddenly stopped. I don't know what's going on. Um. mhm. Mhm. So okay, audio is good. Everything is good to go. We may continue. So we were watching this guy.
Interestingly, E equals mc squared never appeared in Einstein's famous 1905 paper. What appeared was m equals E over c squared. That is, mass is a measure of the energy content of a body. That's the important takeaway. Ultimately, 99% of the mass of objects comes from the energy of the gluons confining quarks inside the nuclei of atoms. They're massless particles, but when they're locked up in the confines of a proton or a neutron, their energy translates to mass. In general, any energy confined in one spot becomes a kind of rest energy of the object, which is what mass is. This is why a hot object is heavier than the same object when it's cold. One philosophical way to think of this is that the entire mass of the universe is nature's way to confine much of the vast energy of the universe in such a way as to make useful particles that can create things and ultimately create conscious living beings like us. The energy needed to keep color-charged particles from existing freely by themselves is ultimately what most of the mass of the universe really is. And this strong force has resulted in life as we know it. Now, one thing that I didn't cover, which is related to the strong force, is the force that keeps protons and neutrons glued together inside the nucleus of larger atoms. This is usually referred to as the strong nuclear force, and it's distinct from the strong force, which keeps quarks glued together. This is also a form of potential energy and also makes up part of the mass of an atom. So let me cover that briefly here. As I described so far, the strong force mediated by the exchange of gluons holds charged quarks together inside a nucleon, that is a proton or a neutron. But if a quark is pulled out of a nucleon far enough, the potential energy created by that stretch is enough to create a new quark-antiquark pair. When this happens, the stretched quark drops back into the nucleon, but the quark-antiquark pair—
Oh, it's a meson. It's not a pion. So why did PBS Spacetime call it a pion?
forms a short-lived new particle called a meson. This meson has a slightly longer range than a gluon, typically about the diameter of a nucleus, so it can be exchanged between nucleons as a force transmitter. This force, transmitted by mesons in the nucleus, is the strong nuclear force, and it holds protons together along with neutrons against their electromagnetic repulsion. This force, or energy keeping the protons from flying apart, is also part of the mass of atoms. It is considered a residual effect of the strong force. In fact, it is this mass, that is the mass due to the strong nuclear force holding nucleons together, that has released this energy in the nuclear bomb. The mass due to the strong force holding quarks together is not the energy released in the bomb. So what you're seeing when you see pictures of a nuclear bomb is due to the strong nuclear force. If you found this video interesting, be sure to check out my detailed videos.
Incredible. So it's the meson that is the atomic weapon, which is a remnant of the strong nuclear force. It's not the strong, it's just a remnant of the strong. It's just the meson. It's not the gluon. This is not a gluon. I mean, the gluon is connecting it in the center, yeah.
Short-lived new particle called a meson, or a neutron. But if a quark is pulled out of a nucleon far enough, the potential energy created by that—
I'm assuming it's going to get dragged out because another nucleon is trying to get away. So when another nucleon is moving away, this quark is being dragged out, and the energy of it being dragged out is going to cause the creation of a quark-antiquark pair.
stretch is enough to create a new quark-antiquark pair. When this happens, the stretched quark—
Boom. The original quark is here. This is a new quark, or maybe this is a new quark, and this is a new, this is the old quark. This is a new quark, a new antiquark. And this is a meson.
drops back into the nucleon. But the quark-antiquark pair forms a short-lived new particle called a meson. This meson has a slightly longer range than a gluon, typically about the diameter of a nucleus, so it can be exchanged between nucleons as a force transmitter. This force, transmitted by mesons in the nucleus, is the strong nuclear force, and it holds protons together along with neutrons against their electromagnetic repulsion. This force, or energy keeping the protons—
So this is a compulsive force. This is the opposite of repulsive is attractive force, because basically this neutron pulled the meson out, so dragged the proton, and it pulled the neutron in. So they were both grabbing it, and that's how it got created. And basically, as soon as it's created, it should be destroyed. No, the gluon doesn't let it be destroyed. So what happens to it?
Transmitted by mesons in the nucleus is the strong nuclear force, and it holds protons together along with neutrons against their electromagnetic repulsion.
I guess the same way it was created by being pulled, then it's going to I don't know. How does it, I would assume a quark antiquark gets created here too, and they annihilate each other because they're exact opposites. But the gluon would have to be an opposite gluon. I don't know.
This force, or energy keeping the protons from flying apart, is also part of the mass of atoms. It is considered a residual effect of the strong force. In fact, it is this mass, that is the mass due to the strong nuclear force holding nucleons together, that has released this energy in a nuclear bomb. The mass due to the strong force holding cores together is not the energy released in the bomb. So what you're seeing when you see pictures of a nuclear bomb is due to the strong nuclear force. If you found this video interesting, be sure to check out my detailed videos on quantum chromodynamics. I'll see you in the next video, my friend.
Very good video. Very good. Very good. Very good. I see more QCD. So visualizing the strongest force in the universe. Let's see more QCD.
The gravity. When you pick up magnets on a table or use
Okay, the stream seems to be fine, but I'm surprised the stream just died. Mm-hmm. 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 Mm-hmm.
your phone or any other electronic device, it's because of the effect of electromagnetism. Electromagnetism is responsible for chemistry. It's the force that keeps negatively charged electrons in a cloud around the positively charged nucleus of atoms. But the force of electromagnetic repulsion is just as strong as the force of attraction. So if we take the example of the helium atom, which is composed of 2 protons and 2 neutrons in the nucleus, if you do the calculations, you'll find that the protons repel each other with a force of 20 pounds, or about 10 kilogram weight. If you consider that this is a macro scale.
Wow. 2 protons want to push each other with 20 pounds repulsion.
Force within something.
I usually can't watch his videos because I only listen to videos. So it's only when I'm in front of my computer that I can finally watch. And then this is so useful, like so much information, so fast.
Small as an atom, which is 1 million times smaller than a millimeter. It is an enormous force on a quantum scale. And this repulsive force is even higher in some bigger atoms. So if the force pushing protons apart in the nucleus is so strong, what keeps them glued together so tightly? Well, it turns out that the force keeping them together is even stronger than electromagnetism. In fact, it is about 100 times stronger. It is the strongest force in the universe. And physicists creatively call this force the strong nuclear force. And amazingly, we ape-brained humans happen to have figured out how this force works pretty darn well.
You see, when you're trying to pull this guy out, you're actually pulling on the entire nucleon. You're right now pulling it.
It's really strong, but works only at very short distances, and it's also a very colorful force. That's why its study is called quantum chromodynamics. In other words, it's the quantum theory of colors. But as you'll see shortly, these are not the kind of colors you're used to seeing. Signs of the strong force. I'd like to thank today's sponsor. About any other streaming service around, you, the people in your life, the month, any 20s, it became clear that the atom was made up of negatively charged electrons. I highly recommend Magellan TV, so be sure to click the link in the description. In the 1920s, it became clear that the atom was made up of negatively charged electrons and a positively charged nucleus. This model, although great in its simplicity, left one big question. If like charges repel each other, how can you pack positive protons so close together in the nucleus? It was obvious that there must be some extremely strong force which can overcome this repulsion. One of the great minds that sought to answer this question was Japanese physicist and later Nobel laureate Hideki Yukawa. He proposed the first significant theory of this strong force in 1934. He realized that since electromagnetic repulsion happens on large scales, for example, we can see its effects in our macro scale world when playing with magnets, the strong force which opposes electromagnetic repulsion must occur on a very small range because we don't see the effect of the strong force in our macro world. Another clue that the range of this force has to be small is because there appears to be a maximum size of atomic nuclei. Any nucleus larger than the size of a lead nucleus is unstable, suggesting that there's a point beyond which the strong nuclear force can't hold the nucleus together. This also suggests that the range of the force must be smaller than an atom. The analogy is like Velcro. If you put Velcro on 2 similar poles of a magnet, if they're close enough, the Velcro will overcome the repulsion and keep them together. But if the magnets are not touching, the Velcro makes no difference. Yukawa proposed that there must be a massive mediator particle that transfers this force between protons and neutrons. Using Einstein's energy equivalence principle equals mc squared and Heisenberg's uncertainty principle, which says that the uncertainty in energy times the uncertainty in time is greater than or equal to h over 4 pi, he solved the equation to find an approximate mass. The range of this force can be found by multiplying c, the speed of light, times the time of the particle's existence. Time, therefore, is just the range divided by c. We can set the range r0 as just the radius of the nucleus. Then by knowing the time, we can find the energy for mass. Plugging in the numbers, we get a mass of about
Incredible. So I present to you a paper that proves conclusively that by my model, which is completely consistent with all of physics, then I can explain away the null result of the Michelson-Morley interferometer experiment. So instead of clapping Nobel Prize! Nobel Prize! No! No! You don't. What's your qualification? What's your qualification? Explain the interferometer. Do you know what the direction of the X and the Y is? It's like everybody, every time I say ether, the ether, it's been disproved. It's been disproved. Really? Here's a paper that says that it has not been disproved. Do you have any questions on the paper? What's your qualification? What's your qualification? Do you have any questions on the paper? Yeah, what's your qualification? Wait, what's your qualification? But here's a paper that Michelson-Morley null result is insignificant. What's your qualification? All right. And this, ladies and gentlemen, is physics. Ladies and gentlemen, I give you physics. That's physics. What is physics? Oh, physics. Did we test the audio? Yeah, I think so. Physics is what's your qualification? What's your qualification? What's your we don't know. What's your qualification? We can't listen to you. We can't listen to you. Okay. All right. Anyway, so now I have a paper. Where did you publish the paper? It's been peer reviewed? Where did you wait? I can't listen to you. It hasn't been published. No peer review. I can't listen to it. Okay. So you have nothing to say when I present you a paper that mathematically shows you where every time I show them a paper, where's the mathematics? Where's the mathematics? Where's the mathematics? It's like they always have complaints. They never. It's just they hate the ether. Oh, they hate the ether so much. Why do they hate the ether so much? Why do you hate the ether? Because it gives too many answers. Too many, no good. No good, too many answers, no good, too many answers. We need to keep the allure that physics is, the universe is even weirder than we thought it could be. Oh, physics is magic. It's magic. Don't take away the magic. Don't take away the magic. No, don't take it away. It's magical. It's not mechanical. It's magical. The ether makes the universe mechanical and they cannot take it. They cannot take it. They hate a mechanical universe. Unacceptable. Let me see. Unbelievable. Unbelievable. There you go. There you go. There you go. Indeed, indeed. Indeed, indeed. Indeed to the power of indeed. Okay. So I'm waiting for someone. That's why I can't go. Oh my god. Okay.
100 mega electron volts, or MeV, and this is remarkably close to what was found later to be the correct answer, which was about 138 MeV. Yukawa coined the term meson to describe this particle. Meson means middleweight. The leptons, like electrons, are lightweight, and baryons, like protons and neutrons, which was about 100. Plugging in the numbers to get a mass.
I see a meson and a pion. Finally, we'll get the answer. All right, so the time. Very nice. Very nice. So this story with the mesons and the pions, and they're allowed. But when I present that the ether is just as mechanical, just as quantum mechanical, it's the same story. It's the same story with particles annihilating, and it's the same story. It's very similar. No, how dare you? No, how dare you? Oh! Okay, all right. So he says here, Hideki Yukawa, Japanese theoretical physicist, 07 to 81. He says E equals mc squared delta E delta T is greater than or equal to h over 4 pi. This is h bar over 2. 1/2 h bar. But delta T, so this is the delta T. Where's the delta E? What is R? The distance? Well, yeah. This is the distance. So let's hear the calculation.
G times the uncertainty of time is greater than or equal to h over 4 pi, we solve the equation to find an approximate mass. The range of this force can be found by multiplying c, the speed of light, times the time of the particle's existence.
Oh, the range of the force. Okay, so c times t gives you the range.
Time,
Okay.
therefore, is just the range divided by c. We can set the
So whatever. So you can set the range if you set the time.
range r naught as just the radius of the nucleus. Then by knowing the time, we
So the energy is the energy of the entire nucleus?
time, therefore, is just the range divided by c. We can set the range r naught as just the radius of the nucleus. Then by knowing the time, we can find the energy or mass. Plugging in the numbers, we get a mass. Set the range, the uncertainty of time is greater than or equal to h over 4 pi.
Okay. This is too fast. I can't. I'm not going to handle it at even a normal speed.
Energy times the uncertainty of time is greater than or equal to h over 4 pi.
Okay.
We solve
So far, so good.
the equation to find an approximate mass. The range of this force can be found by multiplying c, the speed of light, times the time of the particle's existence. Time, therefore, is just the range divided by c. We can set the range r naught as just the radius of the nucleus.
Okay. So he said we can set the range or not to the radius of the nucleus. That's fine, but he replaced the energy.
Then by knowing the time, we can find the energy or mass.
By knowing the time? By what?
Then by knowing the time,
Knowing? Oh, we now know the time. This is the time. So we're done with the time. The change in energy, okay, that's just mc squared, whatever the m is. We're looking for m?
set the range r naught as just the radius of the nucleus. Then by knowing the time, we can find the energy or mass. Plugging in the numbers,
Okay.
we get a mass of about
So the mass is h over 4 pi rc.
about 100 mega electron volts, or MeV.
Oh my god, what is going on? Very interesting. So the mass of the what? What are we looking for? The mass of the I guess the meson. So this is the mass of the meson? Mass of what?
And this is remarkably close to what was found later to be the correct answer, which was
Of what?
about 138 MeV. Yukawa coined the term meson to describe this particle. Meson
Oh, so that's the meson exchange. So that's the delta E delta T that we need to exchange in order to cause an attraction in the nucleus. Very interesting. I guess they did this with the helium. So this is the pi meson. Oh, the pi meson is a pion. Oh, but in general it's a meson. But why is it up anti-down? Isn't it up anti-up?
means middleweight. The leptons, like electrons, are lightweight, and baryons, like protons.
Oh, a quark is a baryon. So I see. So a lepton is an electron. A meson is this guy, is 2 quarks, and 3 quarks is a baryon. Wow. Finally, I'm getting to figure out the names.
Answer, which was about 138 MeV. Yukawa coined the term meson to describe this particle. Meson means middleweight. The leptons, like electrons, are lightweight, and baryons, like protons and neutrons.
So lepton is lightweight.
Meson means middleweight. The
Meson is middleweight.
leptons, like electrons, are lightweight, and baryons, like protons and neutrons.
Oh, lepton is like from the word light. Baryon is like, I guess, I don't know. Bary is heavyweight.
Neutrons are heavyweight. As more experiments were being done in particle accelerators, new mesons and other types of particles kept getting discovered, dozens in fact. This created a kind of crisis in particle physics because it was not thought that these particles could all be fundamental. In 1964, Murray Gell-Mann and George Zweig proposed the very
Every time it's different people. Wasn't it somebody else before? It's always Gell-Mann, but his partner is always changing names.
various mesons and other particles that interacted with the strong nuclear force could be explained if they were composed of even smaller but fundamental particles. Gell-Mann called these particles quarks, from a term in a novel by Irish author James Joyce. Gell-Mann proposed that there were
Finnegan's Wake. Whatever.
term in a novel by Irish author James Joyce. Gell-Mann proposed that there were 3 types of quarks, now called up, down, and strange. The up quark has a charge of 2/3, whereas down and strange have a charge of negative 1/3. All had a spin of 1/2, and they all experienced a strong force. The quark model proposed that mesons were made up of
So pi mesons, pi plus, up quark plus anti-down quark.
quark anti-quark pairs. But
It doesn't matter. It's a quark anti-quark, but it doesn't matter, I guess, if it's up or down. It could be up, up, and down, down. That's what I keep seeing.
another way these quarks could combine is in groups of 3 quarks. These became baryons, or heavy particles, such as protons and neutrons. A proton is made of 2 up quarks and a down quark. You'll notice that these charges add up to +1. The neutron is composed of 2 down quarks and 1 up quark. You'll notice that the charges add up to 0. Other combinations of these quarks.
So this is an actual charge. This is an electric charge. This is not a joke. That's an actual charge. We're not joking here.
Had a spin of 1/2, and down and strange. The up quark has a charge of 2/3, whereas down and strange have a charge of negative 1/3.
So down and strange are basically they are electrical.
All had a spin of 1/2, and they all experienced a strong force. The quark model proposed that mesons were made up of quark anti-quark
There's so much information. This is unbelievable. And he gives it for free.
pairs. But another way these quarks could combine is in groups of 3 quarks. These became baryons, or heavy particles, such as protons and neutrons. A proton is made of 2 up quarks and a down quark. You'll notice that these charges add up to +1. The neutron is composed.
But an electron is completely different for some reason.
Of 2 down
And these are all waves. These things are waves.
quarks and 1 up quark. You'll notice that the charges add up to 0. Other combinations of these quarks form the other heavy baryons. But this had a
I blew her mind away when she said gravity is a force according to Newton. I said, no, it's not. She said, yes, it is. I said, no, it's not. She said, yes, it is. I said, no, it's not. Let me show you the equation. MA equals GMM over R squared. The M's cancel. So A is equal to GM over R squared. And you can see that even light bends. It's not a force. So according to Newton, it's the flow of the ether. And that's how you can, and since Einstein degenerates into Newton, therefore Einstein is the flow of the ether. That's the proper interpretation of GR. The curvature of spacetime is an improper interpretation of GR. So she said, Einstein is curvature. It's not flow. I said, you can interpret. I need to write a paper about this. That you can interpret. That's the next paper. Did I make a note that I need to write that paper? The reinterpretation. The reinterpretation. Let me see if I can find it. Where's the recent drive? So this is in progress. The reinterpretation of Einstein's stress tensor into a fluid stress tensor. So Einstein, you could say, is a solid state tensor, solid stress tensor, but you can reinterpret any solid stress tensor as a fluid stress tensor that describes the stresses that a fluid experiences and the strains, which is the curvature. The stress is the mass and the energy, and the strain is the curvature. So you don't need that. You can I think that is my final frontier. If I can do that, if I can reinterpret Einstein's stress and strain tensors into fluid stress and strain tensors, then I'm home safe. So energy is the, or mass is the stress, and the stress is the annihilation of ether. And the curvature is the flow of the ether. But the stress first is the annihilation and the pressure, the combination of the annihilation and the pressure. Einstein doesn't have the pressure. So my model is just a little different, and that's why my model predicts dark energy. It kills them when my model gives dark energy. Oh my God. It's the last thing they want to hear. The last thing that my crazy ether predicts. You don't know what predicts means. Okay, well, it needs. My ether cannot work without dark energy. Does anyone else have such a theory that needs dark energy? I don't want to talk to you. I don't want to talk to you. I don't want to talk to you. I'm not going to let you talk. I'm not going to let you talk. These poor souls, you're teaching them bad physics. I'm not going to let you talk. Unbelievable. Unbelievable. They're losing their minds. There it is. Can we interpret GR stress tensor as a fluid mechanics stress tensor? So I just copied everything from. Oh my God. I'm so tired. I'm not going to be able to hold on. I'm going to have to tell that guy that I can't. That this is unacceptable. He said. Anyway, let's hear what he says.
major problem, and that is the idea of having three quarks within the same particles. This, according to quantum mechanics, should be impossible because at least two of them would have the same quantum properties. And according to the Pauli exclusion principle, two fermions like quarks with the same quantum properties cannot exist in the same location at the same time. This principle is the reason you can have only two electrons in any atomic orbital, because the electrons can have a spin of either plus 1/2 or minus 1/2 spin. If you put three or more electrons in the same orbital, it would have to have a spin identical to one of the already existing electrons in that orbital. But one of the detected particles, called a delta particle, was composed of three of the same quarks, up, and up, for example. In that case, since these particles all have a spin of 1/2, we can have one particle that is spin plus 1/2, one that is minus 1/2, but the third one would have to have either a positive 1/2 spin or negative 1/2 spin, making it identical to one.
Anyway, that's going to be the final frontier. If I'm going to be able to clearly, easily explain the GR equations, Einstein's field equations, in terms of fluid mechanics, that's it. Then I'm home safe. So I asked ChatGPT, can I do it? Can it be done? So can I reinterpret? Can I interpret or something? Interpret. Yeah, no. Maybe interpret, no? So what is it? Oh, interpreter. Interpret. Oh, can I interpret GR's stress tensors as fluid mechanics? Well, I guess stress tensors as well. So this is the curvature of space-time. Can I interpret, let's write it, general relativity's curved space-time stress and strain tensors as fluid mechanics stress tensors I would even say ether flow. Ether flow fluid model. No. Ether flow model fluid mechanics stress tensor. Something like that. Yes. You can interpret aspects of general relativity stress energy tensor in a way that resembles certain fluid mechanics models, including some concepts found in ether of fluid-like models. However, there are important distinctions to keep in mind, as general relativity fundamentally describes space-time curvature, not a physical medium. But let's explore how these two frameworks align in specific ways. Similarities between general relativity and fluid mechanics. The stress energy tensor in general relativity describes a distribution of energy momentum, pressure, and stress in spacetime and plays a similar role to the stress tensor in fluid mechanics, which describes the stress due to fluid's internal pressure, viscosity, and flow. Okay. Limitations. Well, there are While there are analogies, GR fundamentally differs from fluid mechanics in several. Okay, no physical medium. Yeah. The left side, G mu nu, describes the curvature of spacetime, while the right side, T mu nu, represents the distribution of energy and momentum. The equation relates these two quantities without requiring a medium, traditional sense. Well, so for me, so this is the stress and this is the strain. So the stress times something is equal to the strain. So the stress, right? The stress. I'm trying to think. What would the stress be on a fluid? So in my model, I have the ether being annihilated. This is the annihilation of the ether. The more activity you have, the more ether is being annihilated. Or is this the annihilation and the flow? Maybe this is the annihilation and the flow. And this, no, something has to, this is the cause of the annihilation. This is the mass energy. So it's the same source. The mass energy causes the annihilation of the ether. Once the ether is annihilated, you have, no, this is the flow. The flow is the result of mass energy, of the stress. The stress is the same. The cause is the same. The difference is this, the curvature of space-time, or is it the flow of the ether? So there's no difference. I don't see the difference. This is something causes flow, and that's it. I mean, you don't have to see it as curvature. Why would you want to see it as curvature? Right? Everything you see as curvature, you can just reinterpret it as flow. And that's it. It's just the flow. It doesn't matter what's causing the flow, that there's annihilation and there's pressure and therefore there is a flow. At the end of the day, there's a flow. And that's it. This is a field equation. There is no annihilation here because it's not a quantum mechanical interaction. So there's no room for the annihilation. Therefore, you cannot derive dark energy directly from this. Dark energy has to be imposed on it. Fascinating. Finally, I understand it. Okay, so it's really very simple. And actually, I'm not the first one to do it. Right? I think Dialect. Didn't Dialect do this once? Didn't Dialect do this already? What? Chinos? I figured.
Yeah, I just wanted to say that you're not streaming on YouTube.
I'm not.
It's
I am. It says that I am.
Really? Like your stream is like I clicked your stream and it says it's over past after 1 hour more or less or not. Oh,
I restarted.
so you started a new one.
Yeah, it stopped. I don't know why it stopped.
I didn't get a notification for this one.
That's strange. I don't know. Something is weird. Probably an issue on their side on StreamYard or YouTube. I don't know. Maybe YouTube. So I figured out I figured out how to reinterpret Einstein field equation as the flow of the ether. Yeah. And then I remembered I'm not the first one. So this is very simple. So the T is the stress. Okay, the stress is just the mass energy. And the G is the strain or the curvature. But instead of curvature, you can just say it's the flow. That's all. It's just reinterpreting. It's identical, right?
T is like the energy per volume, right? Isn't that what the T is?
It doesn't
20
matter.
joules
It,
per
it
meter
doesn't.
cubic.
It doesn't matter what it doesn't matter. I mean, T is the stress, energy, momentum, pressure, everything that causes gravity, right? If you have a lot, right? What is mass? Mass is energy. It's just, for example, it's a bunch of gluons seething inside the what are the between the quarks of the neutron. So they're jumping around so much that that they're causing mass, the illusion of mass, which through this factor it causes the curvature of space-time or the flow of the ether. It doesn't matter. I don't have to, right? This is Einstein's field equation. This is let me just finish. Let, let me just I'll answer a question, but let me just finish. This is not a quantum mechanical theory. This is just a field equation. You can interpret any way you want. At the end of the day, the curvature is what we call gravity. But it doesn't matter what it doesn't matter. It's just gravity. It's fine. I mean, this field equation doesn't care that there's curvature or flow. It's what we call gravity. Now, you could say that it's important. It doesn't matter. Right. So anyway, what did you want to ask?
Yeah, but yeah, the general relativity isn't a theory of the quantum theory, but Einstein just couldn't really interpret certain things. That was his issue because he really didn't like quantum mechanics. But you know that already.
No, fine. But I'm
But-
saying no. But that's okay. So this is not a quantum mechanical theory. This is a field equation. It's just a field equation. It's not even a theory. It's just a descriptor. It's a very concise, nice descriptor that mass causes gravity. Gravity is, you can say it's the curvature of spacetime, or you can say it's the flow of spacetime. You can say it's the flow of spacetime. You can just say it's the flow of spacetime. And even that makes more sense than the curvature of spacetime. You could say it's the flow of spacetime. You don't have to say it's the curvature. You can say it's the flow. Even that makes more sense than Einstein's interpretation. The right side, I'm not changing the right side. The right side is staying the same. The right side is still mass, energy, and all the things that cause the curvature of spacetime, or more correctly, the flow of spacetime. Is the flow. You just don't interpret it as the curvature. Just interpret it as the flow. It's really very simple. But it's not the flow of spacetime. It's the flow of space. It's just the flow of space. Anyway, it's just the flow of the ether. The fact that you have time dilation, that's because we already explained that the flow of the ether causes gravitational time dilation. Anyway,
like if quote unquote virtual particles are exchanged faster or
no, I
or
don't have.
slower.
No, there's no there's no gauge boson. There's no particle exchange in my ether theory. My ether,
Yeah, you don't need that.
the
but-
gravitational part is just the flow of the ether. The ether is just flowing and dragging things. But that's the quantum mechanical
Yeah, but,
part. But that's the quantum mechanical part.
going-
But I'm saying
yeah.
that's just the quantum. I don't have to talk about quantum mechanics when I explain Einstein's field equation. Einstein's field equation is just a descriptor. It's not a mechanical theory. It's just a mathematical descriptor. It's like when you have a river, so you can have a field equation that describes the flow of the river. But the fact that the river is composed of tiny water molecules, that's not in the field equation that describes the flow of the river. The Navier-Stokes equations that describe the flow of the river, they're not mechanical. There's no, they don't describe the actual interaction between the molecules in the water. That's a separate, for that you need a separate, separate equations that describe the interaction of molecules, which are particles. But the Einstein's field equations just describes the flow of the river. And you can have like a suction pump, and you can have like you have a pump. A suction pump, that's the mass that causes the river to flow into the sink. So the mass, the T tensor, the stress tensor, is the sink, is the suction, is the vacuum pump that pulls water inwards. And the fact that you have that the water flows, that's Einstein's, that's the G stress tensor or strain tensor. It's called the strain tensor. It should be renamed as, the T is the stress tensor and the G is the strain tensor. And the strain tensor, you can reinterpret it as anything you want. Is the flow of space, I think. Anyway, but I'm not the first. But I'm not the first one to do.
And time comes as a consequence of that.
So for me,
kind of like your rubber ducky.
Right. For me, time, I get time dilation because when you move through the ether, your clock slow down. But dialect interpreted general relativity as the flow. They did the same thing in that episode. The true cause of gravity, it's the flow. They made fun of everybody else. Let me show you. They made fun of and they went through the entire episode.
Yourself.
Let me just lower the volume.
Which causes it.
They went through the entire episode. They didn't in the beginning. They hinted what they're going to,
namely, you're likely to
how they're going to interpret it. Let me see. In the very beginning, they showed how they're going to end up interpreting it.
It's still such a mystery to us. What is it? Where does it come from?
Where does
if you ask YouTube these questions to come across and almost as mysterious as they come from, what is dialect, with general relativity defined, often eludes clear interpretation, of which erroneously
Gravity does not warp the flow. Called gravitational time dilation.
Cool and convincing.
This causes the clocks
On a space-time diagram,
So everybody says gravitational time dilation is what causes gravity. Oh
leads
my
to a
God.
time
Streams near it.
rotate towards it.
object will want to
Upon hearing this explanation, mass and they come together. That's gravity. It all
Let me just
seems to make so much
let me just show you.
sense. Is the whole and which
Because
what time admitted he was reason for your
They
confusion is
spent
simple.
the whole
You're confused
episode. Why isn't it stopping? They spent the whole episode making fun of everybody, showing how everybody can't be
because
right.
one of these videos did
That the explanation doesn't make any sense.
there's a beguiled. Now before curvature and gravity are one. Meanwhile, gravity you have no curvature.
And they're going to reinterpret curvature as flow.
You have gravitational attraction. It is not the cause of apparent phenomena. These two of these videos succeed to a uniform gravity. That time dilation,
Any difference will do. Moves faster through.
a uniform gravity,
Let me just
With the gravity
find
note.
it.
gravitational space, ungravitational field, dilation gradient, time dilation, seeing space, curvature, which dependent phenomena. No matter what, because they return to the surface. So ever, from the perspective,
So
you-
I don't.
that might happen. Fraction.
Yeah, as far as I
Ground
remember,
accelerator, both its top
only at
and
the
parent.
very end
He's a
they
YouTuber.
showed it.
Diagram, video, channels,
Pipeline showed that for that point on a time grid space-time. It
where clocks between coordinate grids, actual space-time, plates, curved line, physics through it. It is not an A, more, legend, or die. Note that. Separation distance, a bunch of. Next, the observer staggered that is
Anyway,
the separation
hold on.
that is separation and others idea back poop the trail goes specification of action gravitation. Then what's an energy density? Act you can its name might lead you asking yourself since this video. Well, to explain that, you say is accelerating. In fact, such massive space-time.
There it is.
Hence, we have the appearance of a universal attraction affecting all bodies, because every single mass in the universe is literally accelerating towards every other single mass.
You see, they're
Granted, this is a very
showing,
abbreviated explanation, but it's a much closer step towards understanding the truest cause of the attraction between.
and this was one of the first times that I said to myself, yeah, that finally somebody's making sense. This is the first time somebody had an animation as if something is flowing into the planet.
Now, such masses don't blow apart into 100 pieces, because real gravity, space-time curvature, steps in here to ensure the space-time manifold is warped in just the right way as to compensate.
You see, it's what? What are you saying? Well, you can't see it? Oh, yeah. Yeah.
For all that outward acceleration, and thus produce a stable configuration.
Wait, what?
I'm working as I talk to you, so
Yeah, I
it's
understand. I
divided
know.
attention.
Yeah, I know.
Yeah, it works like yes, it's kind of like a mix of flow and bend of space-time.
No, there's no bending. There's no bending. It's just flow.
There is like bending. There is
No,
like
no,
you
no.
can
There's no
see-
bending.
you
Nothing
can
is bending.
interpret that
No, there's no bending. It's called it's
or
fluid.
stretching.
No, there's no stretching. No, if there's stretching, then you don't have gravity. No. It's an incompressible. The ether is incompressible. Anyway, you see?
Yeah.
Oh wait, let me just share it.
Literally accelerating towards every other single mass. Granted, this is a very abbreviated explanation, but it's a much closer step towards understanding the truest cause of the attraction between bodies. Lastly, we'll note that there is a way.
Because in the entire episode, they're trying to say that you have to assume that as you're sitting on Earth, really, the Earth is accelerating upwards.
Oh, that's expanding.
Yeah, the Earth is literally, it
right.
must be expanding. So therefore, space must be falling. So it's either you say that the Earth is going up or space is falling down. So they left the arrows going out and space falling down, right? They did both. They're still confused. They're still confused.
Single mass. Granted, this is a
Incredible.
very abbreviated explanation. The space-time manifold is warped in just the right way as to compensate for all that outward acceleration, and thus
You
produce.
see, they're saying I'm going up because space is falling down. So why do you have to say that I'm going up? This is complete nonsense. The whole thing, Einstein's entire equivalence principle is nonsense.
Produce a stable configuration.
The entire equivalence principle, I think, is nonsensical. You don't need it. The equivalence principle, I just have to switch to you so that they can hear you. The equivalence principle from Einstein is that you cannot know whether you're sitting at home and being pulled down by gravity.
Oh, right.
Yeah. Anyway, so I was just, yeah, I had some interesting debates, but the people get so upset. I'm writing more every time I write another paper, so they get more upset. So I wrote the paper why, according to my ether model, we should have expected the Michelson and Morley to get the null results. And this drove them into insanity. They lost their minds. They were like,
Imagine if you were an academic trying to do this.
oh, for sure. They had objections. Every objection. Where did you publish this paper? Where did I need to know that it was peer reviewed before you show this to me? One guy says, and another guy says,
It's like,
"What?
why do you need that?
I don't know.
Can't you do that? Like,
I don't
you-
know." And then
it's
and
like-
then I don't
like
know.
If you know the topic, you can do the peer reviewing.
I know.
Really.
And then he
Like,
says,
that's what peer reviewing is.
and then he says, "What's your qualification? What's your qualification?" Like all the nonsensical And then I start presenting the Michelson-Morley. Explain to me the Michelson-Morley experiment. Where's the X and the Y? You don't know what the X and the Y is. Goodbye. It's like, And finally, there was one guy. His name is Piotr, some Polish guy. He wouldn't let me speak for like an hour. He would not let me talk. He said, "I'm going to protect everybody in the room from you, so they don't hear your nonsense." Yeah.
What?
What?
That's weird. Yeah, that's
Weird?
weird.
Weird. And then at the end, I had to take it down. I had to take down the video because there was. I keep getting spammed. People send me, bad videos. That I got a terrible video. Jesus, I'm PTSDing because of the video that I saw. So I'm waiting for the stream to. I need to edit out the last 1 minute of the stream, and then you'll see
That's
it.
so strange that people get so emotional about this.
It's unbelievable. It's like worse than Trump derangement syndrome. You know how people go crazy
Yeah, I
because
know.
of Trump. This is
Yeah, like,
worse.
I understand that. Like, I yet people watch like some
No, no,
TV and then
no, no,
they
no.
talk about
I'll
people
tell you.
have
I'll
an
tell you.
opinion.
I'll tell you. No, no,
Yeah.
no. I'll tell you why they hate the ether. The ether. We discussed it. The ether answers too many questions, and it takes away the magical universe. These people, they are mystics, and they love the mysticism of the new age of physics. They love the mysticism, and I'm taking away their mysticism. I'm taking away their mythology. I'm taking away the
I think
magical.
it's more than that.
No, no, no. No, I don't think it's more than that. Well, it's
I think it is more than that. I think it is like I think they're afraid of like not being as smart as they think they are.
I don't. It that's. I don't think that's it. I think they don't.
I actually do think that's it.
No, I don't think so because the actual smart ones, like the smartest one, the Capioca Weasel, he's the nicest one. He never attack. He
Yeah,
always.
exactly, because he's
So
more secure.
no, but he's the smartest. So it's nothing to do with being smart. It's that they
No, but like, see, no, but that's what I'm saying. Like, it's not about being smart. It's about thinking you are smarter than you actually are.
no. But
It's about
he
not being smart.
no
So Piotr
no
doesn't have a problem
no
with
no
with
no no
his
no no no.
security.
It doesn't make any no. So like when I talk to a lot of them are idiots. A lot of the people in this room, they're globers. They're not as crazy as the flat earthers, but they don't know physics. These people don't really know physics. Like Sean G, he doesn't know physics. He barely knows anything. But when he hears me, he hears truth. He knows that what I have is something very powerful, and he cannot accept it that he's actually seeing someone revolutionary in front of him. This is too much for him. Like for him to actually think, whoa, it's either I'm talking to an actual super Einstein or this guy is completely wrong. Because if I'm right, then I'm super Einstein. So I must be wrong because there's no way I'm super Einstein. That's impossible.
I mean, it's also like a weird worldview.
What? It's a weird worldview?
Einstein, was like a very
Yeah.
strange worldview. Because Einstein was like someone, like he was smart, of course. He was very smart.
Yeah, he was
He
normal.
was just a person, like
Yeah, it was
as
a
much
and
of
he
a brain
made
as everyone
and he
else.
made many mistakes. He said there's no black holes,
It's
no
like,
gravitational wave.
and
He
no one
made so many mistakes. It's like he didn't.
Yeah,
And of course
no one
he.
should like give him shit for that, right? Like
What?
it's normal. He's just a human being.
Yeah. It's like, but in their eyes, Einstein is like beyond God. That there's no way somebody can be as revolutionary or even more revolutionary than Einstein. Like I'm answering too many questions. I'm answering the particle wave duality and dark energy and gravity, and I'm simplifying everything. Everything becomes so simple. That's impossible. Like I must be, and some of them say it. They said, what makes you think? They asked me, what makes you think that you're a bigger genius than all the greatest geniuses of the past 100 years that have dedicated their lives to this and couldn't figure it out, and you figured it out in a few months? What? How?
Yeah, I mean that's legitimate to ask, but it's not. It's just the framing is not correct, because now we have access to a lot more information than they did.
Yeah, that's also
So
true.
it's a lot easier to figure out
That's
these
true.
things than it was back then.
Yeah, that's also true.
The question is, like, lots of people get stuck on previous theories, and
But I see that's
and
the
then they don't make progress.
so a lot of people what happened with me is
You know what you're doing is let me just say, what you're doing is like perfectly fine. It's just out inside. You build some hypotheses, and then you check if they you build upon them, and then at some point you check if they actually work, if they don't work, if we need to change a thing or two. Yeah, that's how you do it. But now we have access to a lot more information. That's
it's
the
not
good thing right
it's
now.
not it's not the information. It's I decided, like, for years I couldn't understand anything. I didn't understand anything. Nothing made sense. I was listening to Professor Sean Carroll and to everybody. I was listening, and to Einstein. I couldn't make any sense of anything. But 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 deep down I felt that it must I felt that I have a better, simpler understanding compared to everyone. I felt that I know what's inside a black hole, and slowly I got a better and better feeling for what's inside the black hole and how the black hole works. And then one night I decided, tomorrow morning science is mechanical. No more wave probability distribution of the electron. No more. No more. I'm not going to accept that. The universe is going to be mechanical starting tomorrow morning. And I went to sleep. And I woke up the next day, and that's it. And I sat down and I said, why does the apple? I was curious. Okay, now that I decided to redefine physics and science, then why does the apple fall? And the only explanation is something must be. Oh, and then I was doing anyway, and then I started and I said to myself, I have to figure this out. Everything has to be. But once I made the assumption that it must be mechanical, which means it must be quantum mechanical, everything fell into place. You saw it in front of your eyes. You saw, and the cherry on the top is that my ether requires that the universe will go under an exponential inflation. So I'm the only theory in all of science that predicts exponential cosmic inflation. No one has exponential cosmic inflation in their model. My model requires it. It comes directly out of the ether. So it simplifies all of physics. It doesn't contradict any physics. It gives you instantaneously special relativity, general relativity, quantum mechanics, wave particle duality is resolved, everything is fixed, dark energy predicted, black hole analysis instantaneous. It's like it's magical. So you're telling me it's wrong?
Yeah, I mean, it's a good theoretical foundation for sure.
It's
Like,
amazing.
to explore.
I mean,
Yeah, and the calculations and all of that.
everything becomes so simple. All of physics become all of modern. All of modern.
It's great. Like it's great. Like it's just like people are so close-minded.
No, it's not closed. I don't think it's closed-minded. It's like, you know how Aristotle or Plato,
Kind of like envy as well.
What?
A lot of things.
Yeah, envy too.
Kind of like envy as well.
Yeah, but envy too. But this is Plato's cave. So when the guy came back, when he came back to the cave, they plucked out his eyes because he kept telling them what he saw outside, and they said, No, no. That's it. They said no. They plucked out his eyes, which is too late because he already saw what's outside. But they couldn't hear what he had to say. No, we're not interested. We're not interested in more information. We like the shapes, the crazy shapes on the walls. We like it. And he gave them a simple mechanical explanation why there's these shapes on the walls of the cave. No, 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 we're not interested. We're not interested in the cause. We like the effect. It's good enough. Don't confuse us with the cause. So this is
Yeah, I
so.
like how Plato. How long was that? Like,
Oh,
that's
it's
so
a.
long ago.
This is
That was like
a long.
supposedly over 2,000 years ago.
It's probably 2600. Yeah. Yeah, yeah.
Yeah,
And
something
he
like that.
and
And it's still the same. It's like
the-
nothing has been learned.
yeah, nothing. Yeah, they still. Yeah. This is incredible. This is absolutely.
Yeah,
And
it's
every
quite,
day.
quite amazing.
And every day I come to them with another paper because every time they tell me something else, oh, you don't have this, you don't have that. So, I started telling them that's another paper, that's another paper. Like everything is a paper. Everything is a separate paper. And that's such a convenience that everything for me is a separate paper. So, it's like otherwise everything would have to be one long paper. I don't like writing one long paper. It's much more convenient to have separate papers. So every time they ask me, "What about this? What about that?" I'll come back to you. I'll write a paper. I'll present the paper. Everything in time, in due time. Anyway, so but yesterday was incredible. For hours he didn't let me talk. He said, "No, I'm going to be banned from the server in order to stop you from contaminating these people's minds. No one is allowed to hear you." Literally, this is the way he was talking.
Weird.
And I said, "Why? What do you want?" "No, no, no, you're not gonna talk." He said, I don't mind flat earthers as much as I don't like you. As much as I
Wow.
and I'm showing them papers. Here's a paper. Here's all the calculations, every calculation exactly. Here's the numbers. Here's exactly how many wave shifts we should have predicted that Michelson and Morley should have had with my ether model. And the answer is 2 times 10 to the negative 5 wave shifts, meaning it's 100 times. They needed equipment at least 100 times more sensitive. At least. They had 10 meters, they needed at least a kilometer. They had a 10-meter interferometer, they needed at least a kilometer. At least. The very least. Probably more like 10 kilometers. A 10-kilometer interferometer will show you the 350 meters per second. But I think I think predicts this flow. Because I think this is the Gravity Pro B. You remember we discussed Gravity Pro B?
I do remember discussing that. But what was that exactly?
It's basically it's the frame dragging. It's the frame.
Oh, I see. I remember that. Yes. I
So
fell asleep in that.
so I think anyway I think
I remember it. Yeah.
it should GR should be able to predict it. If they were able to predict frame dragging, I think this is the same effect as frame dragging. I think it's the same effect. Anyway, look, I'm having a good time. I'm writing papers, but I want to sit with you and continue doing the AI. I want to work on AI with you because we're done with this. We're gonna finish writing the papers. I'm gonna, and that's it. I want to put your name on some of the papers. The rubber ducky, you should have your name on it because we worked on it together. I'm done with these papers,
Okay.
and I want to do AI because if you think
Just mention me. Fine.
if you think I
As a
have
collaborator.
if you think I have good physics, you haven't seen what I know in AI. In AI, I am literally number one on the planet. I mean, physics apparently too, but
Okay.
in AI, I mean, that's my field. I am grandmaster in I mean, in actual intelligence. Like when it comes to actual intelligence, I am the ultimate grandmaster. So
Okay. Great.
yeah,
Yeah, I would like to do that. I've been meaning to try to do that for some time, but I never really have time to end up dedicating to
so
that.
get your headphones. Get good headphones so we can talk on the train, and then we can have an hour on the way and an hour on the.
I got some headphones. Yeah.
Okay, so I'm gonna go to sleep soon. I'm waiting for somebody to come, but he's not coming.
But I'll
Um,
be working from home for most of the time, I think,
yeah, I
for
know,
for this week.
but when you go home tonight, we'll be able to work.
No,
If
I'm
you
home today all day.
oh, until you go to sleep, you're gonna be working.
Uh, yeah, but we can talk a bit.
Okay, I just want to finish watching the ChatGPT, and then I want to start building our own model. Our model is going to be a little bit different, but first I want to build something simple, and then we'll do the actual revolutionary stuff. It's going to be completely different. I mean, not completely, but different enough. Different enough that no one has done it. Our performance will be light years ahead of everybody else. Anyway, you going back to work?
I'm working, so it's fine. I'm working and communicating with other people from work.
Oh, nice.
So and yeah, so it's fine. I can stay for a bit.
Hmm. I'm hungry. I'm gonna take a break to get a protein shake and call the guy that's supposed to come. All right. Let me cut the stream. All right, cutting the stream.